everyone to this lecture on side and covert channel attacks, in particular with a focus on Meltdown and Spectre. Okay, so as I sent email, there's a slight detour in our proposed plan. The plan was for today was for me to cover a paper called SCONE today, which is SGX plus Docker. And my students are actually preparing a lecture on Docker containers. Unfortunately, it's not going to be ready in time for Wednesday. It's going to be ready by next week. So they will be presenting the lecture, and I will be putting up material as well as a GitHub link for you to play with the code. So I thought I will do containers and then I will do SCONE. So probably I will reshuffle the lectures after side channels. We may move to ARM trust zone before we come back to the topic of containers and SCONE. Okay, so bear with us as that lecture gets ready. In any case, right, so today's lecture is on side channel and covert channel attacks, and in particular the Meltdown and Spectre attacks, which I'm sure many of you have heard about. These were in the news big time 3 years ago, early 2018. And the key thing about these attacks is that ever since they were announced by the researchers who did them in early 2018, and it's only relatively recently, right? 3 years is not too long a time ago. This has spurred essentially a cottage industry of these kinds of attacks, which are, as you will see, the name side channel and covert channel attacks, you'll see where they come from. To the extent that now almost every other week there is a new kind of attack that is based on similar concepts, right? So it's very important that you understand what these things are. And so today's lecture will be an introduction to side and covert channel attacks, which have major implications in cloud security as well. But by no means are the two attacks, Meltdown and Spectre, considered the state of the art anymore. Of course, they're still applicable, they're still as dangerous, but the state of the art has moved on to much scarier things right now. We will not be discussing those. We'll just be discussing the basics, because even these attacks actually takes some time to understand. It's very, very elegant, and it sort of helps you understand the attacker mentality. Okay, how people think, how the attackers think with respect to exploiting the system. Okay, so what are side channel and covert channel attacks? Let me first tell you about that before we get into the details of these attacks. So a side channel is an information channel between two parties, by which, so let us say that there is a side channel between Alice and Bob, but that Alice and Bob are two entities in an enterprise that are not directly allowed to communicate with each other. Okay, so for whatever reason, Alice and Bob do not have a direct communication channel. Bob cannot directly get information from Alice. Okay, but a side channel is some mechanism that Alice and Bob decide upon, which is enabled by certain features of the computer system on which both of them have an account, through which Alice sends information to Bob. Okay, so here is one very simple example, right? Maybe you and I are not allowed to talk to each other during the exam. Okay, but you and I, nobody stops you from looking at me, and maybe this is an objective style test. Okay, and for every question you're going to look at me and blink once if the answer is A, blink twice if the answer is B, blink thrice if the answer is C, and blink 4 times if the answer is D. Okay, so all I have to do is, after every question, look at you, you blink once or twice or 3 times or 4 times, and we have been able to cheat, okay, without you ever talking to me. So that's an example of a side channel, okay, where both of us are cooperating to achieve some malicious end goal, which is for you to communicate with me via a channel that I don't even realize exists. Okay, we are not explicitly allowed to communicate, but we are implicitly communicating through this channel. Okay, and this channel over here is me being able to look at you. All right, so that's a side channel where both the people at the end of the channel are malicious and collaborating. So a covert channel is one where one of the parties is not collaborating in the sense that one of them is the victim and the other is the attacker, and the attacker is able to extract information about the victim through the covert channel. Okay, so in particular, we are going to be looking at Meltdown and Spectre, which affect all Intel processors. Okay, and you will see that it's extremely dangerous, and Meltdown is what we will be looking at in a lot of detail. Spectre I will be covering at a very high level because Spectre is a much more harder attack to describe than Meltdown. Meltdown I can describe in the space of 5 lines of code, and so we will look at the actual assembly code of Meltdown and try to understand Meltdown in its entirety. Now, the thing about Meltdown and Spectre is that there is a defense for Meltdown that people have proposed. It's a software-based defense. It has its own costs in terms of performance overhead. So there is hope as far as at least preventing Meltdown goes. As far as preventing Spectre goes, there is no hope, and you will see that. In fact, it is. Well, people are proposing in the research community, of course, but there is no practically deployed solution to Spectre yet, and it doesn't seem like there are any defenses on the horizon yet. Okay, and just to give you an idea of what Meltdown is capable of, just look at the title of the paper that is assigned as reading for you today, which is what Meltdown is. Right? So Meltdown is an attack that allows user space processes to read kernel memory. Okay. Now, as you know, in any process virtual address space, the kernel is also loaded. Approximately 1 gigabyte is occupied by the operating system kernel. And the way that the processor provides protection for kernel memory is that it ensures that kernel memory can only be accessed when you are in the kernel mode of the processor. That is, you would have had to make a system call and be in the kernel in the context of that process in order to be able to access the kernel's memory. So what this attack is going to be able to accomplish is that it's going to allow the user to access kernel memory without such privileges, without actually having kernel privileges or without the processor being in the kernel mode of execution. And so what happens when a user process can read kernel memory? When a user process can read kernel memory, remember that the kernel is managing all other user processes on that system. So any attacker on the system can read the secrets of all the other processors, of all the other processes that are running on the same system. So for example, maybe there is a browsing session in which you are entering your password and there are cookies saved and so on. An attacker process that's running on the same system, you might not even know that the attacker process is running, can actually tap into that session and record everything. Okay, so it's as dangerous as that. It does not get worse than this. Right? So Meltdown is an absolutely devastating attack. Spectre can do the same, right? So Spectre is not an attack that reads kernel memory from user space. Rather, Spectre allows, using Spectre, you can break out of sandboxes in browsers. Okay, so for example, the JavaScript on your browser that's running on your browser that is constrained by the same origin policy sandbox that's in your browser, you can use Spectre to break out of that. Okay, so what that enables is, of course, once you break the same origin policy, all of the attacks that are possible if you don't follow the same origin policy are now possible. Okay, so it's extremely devastating that way. So let us start off with Meltdown, okay, and then see how these attacks work, right? So we will sort of understand the attacks in full detail. So I must tell you that side channel and covert channel attacks are not new in the sense that Meltdown and Spectre did not invent the concept of side and covert channel attacks. They have existed they have been defined and been in existence as far back as in the 1970s, right? So you will find, for example, references to side and covert channels using the disk, timing channels, and so on, even in papers and literature that go back to the 70s. It did become popular in the mid 90s in the crypto community when there was a famous paper that showed how to leak cryptographic keys through cache side channels. But it remained a very niche topic. Now, the reason that it has become all the more important is because of cloud computing, right? What you will see in both Spectre and Meltdown is that they leverage shared hardware resources, right? So when you go to the cloud, you are typically renting a virtual machine or a container in the cloud. And the cloud provider is providing you a common hardware platform, rented hardware platform on which you can run your virtual machine or your container. Now, there might be other entities that are also running on the same physical hardware platform. This is beyond your control, right? So it all depends upon how the cloud provider decides to schedule other people for execution on the same physical platform, right? It is the cloud provider scheduling algorithms to maximize their resource usage. It is not really under your control. But what is the problem over there, right? So the problem is that even though virtual machines provide you an illusion that you have your own machine, or containers provide you the illusion that you have your own namespace, you are ultimately running on shared hardware. In other words, you are sharing the memory hierarchy. Supposed to provide abstraction that protect you from or protect your virtual machine from other virtual machines, right? And the way that they provide this abstraction is through the concept of virtual memory, virtual CPUs, and so on. So that abstraction is provided. But at the end of the day, the hardware implements certain microarchitectural features that are not really visible to these abstractions, but nevertheless exist, right? Caches are one such example. Translation look-aside buffers are other such examples. So these features of the hardware that are not really readily visible to the end programmer, at least programmatically in terms of providing programmer access to these data structures that exist within the hardware, they are called micro-architectural features. Okay, so they are features of the architecture that exist to improve performance, but that you, the end programmer, are not really supposed to worry about them. And what Meltdown, Spectre, and the following family of attacks essentially show is that these micro-architectural features have grown to become a giant security problem in the modern cloud computing era. Okay, so that is what the gist of this lecture is. Let's get into the details. Okay, so let me first tell you why these attacks are so dangerous. We have gone over it very briefly, but essentially they allow an attacker to read the contents of arbitrary memory locations on a victim computer. So for example, user space reading kernel memory. So what this means is that you can read anything stored on the machine, stored passwords, cryptographic keys, credit card numbers, everything. Okay, and the worst part of these attacks is that there is no vulnerability that they're exploiting. See, if there was some vulnerability in the software or there was some vulnerability in the hardware, you could fix it. There is no vulnerability. They're just exploiting features of the hardware, right? So that is what makes these attacks so counterintuitive and so hard to fix, because they're not really exploiting any vulnerabilities. They're all features. Okay, and as I was saying, the defense has only been proposed for Meltdown, at least a widely deployed and proposed defense for Meltdown, nothing yet for Spectre. And so it remains a dangerous attack. Of course, now there are also attacks. There's a follow-on to Meltdown and Spectre called Foreshadow, which completely breaks SGX. Okay, so whatever we saw in the SGX lecture, where keys and so on are stored inside the enclave, those keys are now visible to the attacker. So this is becoming a big cause of concern in the SGX community also, and the hardware community is rapidly trying to find fixes and propose successor architectures. So the TDX is one such architecture. But this shows you again the cat and mouse game between the attacker and the defender community. The defender community, for example, the processor manufacturers came up with SGX as a novel defense for malicious cloud providers, and now we have this side channel attacks against this really novel defense. And so now what's the next step in the game? Your guess is as good as mine. Okay, so they're absolutely spectacular attacks. Okay, And the reason that they are spectacular attacks is because both of them exploit tricks that were proposed in the computer architecture community decades ago, to the extent that no chip is manufactured today without these tricks. Okay, so so for any of you that is taking computer architecture this semester or has ever taken a computer architecture course in your undergraduate, you would have at least heard of these names, and you will definitely be reading about them in detail if you're taking the computer architecture course over here, which is out of order execution and speculative execution. Okay, every processor executes every modern processor employs these tricks in order to get performance, and there is no way that a hardware manufacturer will think about ever manufacturing a chip without these tricks sort of embedded in the silicon itself. Okay, of course there are some very, very simple processor designs that use in order execution, but and the attack obviously doesn't apply to them, right? But all Intel processors that you use out of order execution. Every one of them uses speculative execution. Even your phone uses speculative and out of order execution. ARM processors too. So Meltdown exploits out of order execution, and Spectre exploits speculative execution. Now the thing about out of order and speculative execution is that if you turn them down, your programs are going to run between 2 to 10 times slower. Okay, no processor vendor will ever be able to sell a chip that runs programs 2 to 10 times slower. Not in this generation. Okay, not possible. So it's a big problem for all processor manufacturers. Okay, and both of these tricks, as I said, are completely standard, implemented by all modern processors, and there is no flaw in their proposed design or the specification. And in fact, you will not build a modern processor without these tricks implemented. Okay, you cannot just turn them off as a defense. It's just not possible. Okay, that's a non-starter. So that's what makes designing a defense very hard. So I will be talking about both out of order as well as speculative execution. If you're not familiar with it, I will give you at least a preview. Of course, if you're taking an architecture course, you'll be familiar with that stuff. You'll know the stuff in much more detail than I will be covering in today's lecture. Okay, so let's look at the background. There are various pieces to these attacks. So I'm going to be developing the attack as a sequence of building blocks, and then we will compose all of these building blocks together to form the attack. Okay, so the first building block is that of virtual address spaces. Okay, so of course, all modern machines these days are 64-bit, but just to keep the discussion in the class simple, let us talk about a 32-bit machine. A 32-bit machine has a 4 GB address space. On a 64-bit machine, currently only 48 bits are used, so it's approximately 281 terabytes of virtual address space. But the point is that all process code and data are loaded into this address space. And as you can see from this picture, even let's see why my mouse is not showing up. Yeah, so even the kernel is loaded into the process virtual address space, and of course your stack, your nmap region, your heap, and so on. And so the process code and data is loaded into the address space, and every process address space is isolated from every other process address space. So what is the mechanism that ensures this? Well, it's the concept of virtual memory, right? But the key point here from this picture is that the kernel code and data is loaded into every process address space. On a 32-bit machine, it's the top 1 GB. And on a 64-bit machine, it's some other fixed location, but it's not the top 1 GB, but it's there, right? The point is that it exists within the process virtual address space. And so if there are a particular range of addresses in that virtual address space that belong to the kernel, and the kernel space over here, it stores all of the data structures that the kernel typically maintains for all the other processes. All the page tables are there, all the task structs are there, all the memory maps are there, everything is over there within that kernel space. And that is why this kernel space should not be accessible from the user space. You should, if you take an address in this kernel space, and of course you can create an address in this kernel space because you know exactly where it is, but if you try to dereference that address when you're in user mode, you'll get a segmentation fault. The processor will not allow you to access that location. You will only be able to access that location once you issue the syscall instruction, in which case you're within the kernel anyway. right? And the kernel is allowed, obviously, to access its own memory. Um, so, okay, so that's building block number one. This is a concept that's familiar to you all, but nevertheless, let's page it back in. And so the goal, of course, is that kernel memory should be isolated from userland because the kernel contains sensitive info about all the other processes that are running on the system. And on modern systems, there is another take, which is that because of the abundance of virtual memory, which is, on a 64-bit system, approximately 281 terabytes, for purposes of performance, modern operating systems generally map all of physical memory into the kernel address space. Now, it's very rare to find a physical machine that has 281 terabytes of DRAM installed. Nobody can afford that much. Maybe in very, very, very high-end servers. But most modern systems, you generally have just a few tens of gigabytes of memory. Terabyte is also rather rare just because of the cost of memory. But you have, essentially speaking, much smaller amount of physical memory than virtual memory. So it is common practice these days for kernels to actually map all of physical memory into the kernel address space, just so you can reference physical memory very easily. You don't have to bother going through the entire paging infrastructure. You can actually access it directly. This helps the kernel do things much more efficiently. Okay, and you will see that becomes a problem, because now if all of physical memory is mapped to the kernel address space, and you, the end user, can access the kernel, then what happens is that you're able to get a dump of the entire physical memory on that machine, okay, via the meltdown attack. So, as I said, if the userland code attempts to directly access kernel memory, the hardware will trigger an exception just based upon the prefix of the address. If the prefix of the address is anywhere within the kernel space, you will immediately get a hardware exception. Go try it, right? Go try it and see what happens. You will get an exception, a segmentation violation. Okay, so that's one concept. The next concept is that of virtual and physical memory, which you're all familiar with. Which is that the operating system maps each process virtual address space to physical memory, and this is done on a per process basis using page tables, right? So every process has a page table that's allocated for its virtual address space, and the virtual addresses are mapped to the corresponding virtual pages are mapped to the corresponding physical pages where they are currently resident in memory. Okay. If a page does not exist in physical memory, the page table bit will indicate that, in which case it resides on disk and it's swapped into main memory as and when the page. Okay. I think I momentarily lost my network connection. I am back. I hope this is still being recorded. Yeah, it's being recorded. Okay. I don't know why I have got bad network quality in the department. It's very strange. Okay. So where was I? Yeah. So the operating systems. So the page table is part of the hardware-software contract, and the operating system manages it, although it's accessible directly from the hardware. So the kernel itself is mapped into the process address space, and the virtual to physical mappings, the kernel's own virtual to physical mappings, are part of the page table of every process. Okay, so that was building block number 2. Building block number 3, which is also familiar to anybody who has taken a computer architecture course, is the concept of the memory hierarchy. So the memory hierarchy generally resembles this pyramid here, which is that the higher you go in this pyramid, the more expensive that kind of memory, but the faster that kind of memory is. So for example, you only have a few tens of registers in any modern processor, but these registers are typically accessible within 1 or 2 processor cycles because they are located on the chip itself, right? They are right there on chip, accessible from the processor pipeline. Okay, so there is in fact circuitry that directly connects the processor pipeline to the registers, and so you can access them within 1 or 2 cycles. And so access to this kind of registers is extremely fast in the order of nanoseconds. But of course, they are also very expensive because the amount of real estate on a processor chip is limited. So there are only few tens of registers. Okay, you can only store a few, at max, a few hundred bytes of data. Coming after registers, of course, is the L1 cache, which is within the processor chip, but further away from the pipeline. You can access it in a few tens of cycles. And then there's the L2 cache, and the L1 and the L2 cache are generally in a multi-core machine. They are private to each individual core, but the L3 cache is shared across all cores of a multi-core machine. Okay, so you have some private cache levels and some shared cache levels, and then comes physical memory, which is generally not on chip. Although that is changing, right? I mean, with technologies like 3D stacking and so on, you actually have on-chip memory, but this is off-chip memory. So physical memory is located elsewhere, and there's a bus that connects the chip to the physical memory. And then, of course, you have your slow storage but reliable storage like file systems, disks and so on, which are generally extremely cheap compared to memory. So on-chip caches provide fast access to data, and the L3 is also called the LLC. And it's important to note that caches generally store objects at the granularity of cache lines, right? And that generally varies from architecture to architecture. It's 64 bytes on Core i7, for example, for L3 caches, right? So that's the granularity at which caches store data. The point is that anytime you bring something to the L1 cache, at least in an inclusive policy, if you have brought something to the L1 cache, it's also there in the L2 as well as the L3. Okay, it may be evicted from the L1, but it will not be evicted from the L2, not necessarily. Okay, so that's the inclusive policy, and that's just one policy. There are all sorts of variants, but that's one of the more popular ones. Okay, so that was the third building block. Now let's look at the fourth one, which is that of cache-based covert channels, or rather, this is a continuation of the previous one. So let's start by talking about now a covert channel over here, and we will talk about how Alice and Bob can actually communicate via the cache, even though they are not directly allowed to communicate with each other. Okay, so Alice is not allowed to send Bob a message explicitly, but she's going to communicate by sending signals through the cache. Okay, so let's see how this is accomplished, right? So we are going to play a game here, right? The goal is for player A, which is Alice, to use the faster access times of cache memory as a side channel to communicate with player B. In fact, this is going to be actually a side channel attack. The title of the slide is misleading. It's not a covert channel. They're actually colluding, so it's a side channel. Or rather, did I get the definitions mixed up? In any case, right? Side and covert channels are related in that sense. So they're going to communicate, okay? And the trick is going to be to use the fact that in the memory hierarchy, if you're in the L1 cache, memory access times are faster than if you're in physical memory. Or if you're in the L3 cache, it's in a few tens of cycles. If you're in physical memory, it takes around 50 cycles, okay, to access a word in memory. Okay, so the very first thing that Alice does is that she flushes the cache. Okay, so flushing the cache will cause it to become empty, and there are many ways to flush the cache. You can load it with other sorts of data that will cause all of the cache lines to be evicted. But this particular instruction over here, CL flush, can evict cache lines. Okay, so Alice evicts the cache. She can do this in other methods also. She can just read other data that they are not going to, Alice and Bob do not commonly read, and flush everything else from the cache. So it's empty, okay? In other words, if you access now a word of data, it's going to have to be brought into the cache in the first place from main memory, okay? The processor is not able to access the data directly from the cache. All right, so that was step one. So here is what now happens in step two. In step 2, Alice is actually going to set up something called a probe array. Okay, so this probe array is very special in the sense that it is set up in such a way that so Alice and Bob both know exactly how cache lines are mapped. Okay, so the mapping policy of the cache is known to both of them, and that is also generally available, or you can infer it using workloads. But she sets up this probe array in such a way that every element of this array is going to occupy a different cache line. Okay, it's set up in memory. But every time she accesses a different element of this array, it's going to go to a different cache line. That's the precondition for this probe array. Okay, so she sets it up. It's there in memory. And now what player B does is that if he wants to communicate a value X to player A, he's not allowed directly to communicate to Alice. He just goes and accesses the Xth element of the probe array. Okay, he goes and reads it, for example. All right. So he just goes and reads the Xth element. So what happens when you read something that is in memory? Generally speaking, it's brought to the cache, right? The element is loaded into the cache, and then Bob is able to read the Xth element. Okay, so this is a microarchitectural state change. You, the end programmer, never write into your program saying bring it to the cache. It's just the architecture that does it. The processor chip does it. And so there's a microarchitectural state change because it changed the state of this microarchitectural data structure, this cache, from being empty to now storing the Xth element. Okay, so that is how Bob has so he wants to communicate this value X. All he has done so far is that he has read the Xth element. So far, Alice doesn't know that the value that Bob is trying to communicate is X. But how does she learn that value? So now what she does is the following. This is step 4. She just goes and reads every element of the probe array sequentially. And she's going to measure the access time for each element, to access each element of the array. Okay, how do you measure access time in a computer system? So all of you are of course familiar with the time command, the command line. But if you want very fine-grained measurements on a computer system of time, the exercise, the way to do it is using the processor's timestamp counter. And there is an instruction called RDTSC, which allows you to read from the timestamp counter. TSC stands for timestamp counter. And what it gives back to you is the number of processor cycle elapsed since, let's say, some time that the processor was switched on. So you read 2 consecutive values of the timestamp register, okay, and subtract them, you'll know exactly how many cycles elapsed between the 2 accesses to the timestamp register. Okay, and you multiply that by the processor frequency, you can measure the time in seconds or microseconds or milliseconds. Okay, so that's how you measure time on a computer system. And all the utilities basically use that timestamp counter, right? The time command line utility is actually using the timestamp counter. So that's what Alice would do. She would read every element of the array and actually surround that read statement with 2 reads of the timestamp counter and then figure out exactly how much time that read statement took to complete. Okay, so she reads probe of 0, probe of 1, and so on. Okay, so what can you say about the access times of the array? So when she reads probe of 0, that will be brought into the array, probe of 1, that will be brought into the array, and so on, into the cache, and so on. Okay, every one of those accesses is going to take the amount of time that it takes to access main memory. The only access that will take less time is the access to the Xth element, which is already there in the cache, and so the processor will happily evade reading it from memory and just directly serve it from the cache. So instead of taking 50 cycles, it's going to take 10 cycles, and Alice will be able to observe that. Okay, and therefore she will be able to know that Bob is trying to communicate the value X to her. And so now you can see why the probe array was actually set up the way it was. It was set up in a very careful fashion in the sense that any accesses to any prior elements of the array should not kick out the Xth element. Because if they kicked out the Xth element, then Alice will not be able to measure that and obtain a side channel. Okay, so the way you design this probe array goes into the design of the side channel attack and exactly how you set up things for the side channel attack, right? So if you ask me, what happens if this element had been kicked out, I would say that then you have not designed your attack properly. You should design the probe array in such a manner that every element accesses a different element of the cache. Okay, so that's the building block, which is cache-based covert channels. And I'm going to put it all together, but let me just briefly stop here. Any questions about the building blocks that we have spoken about so far? No. Okay, so let's move forward.
What type of, I had a question.
Yeah.
What type of adversaries are Alice and Bob? Are they like different processes or is it something else?
So they are different processes, but then you might now ask me, how did this memory come into the picture?
Exactly.
Right? They could be threads, they could be processes. I will show you shortly. This depends on the context, right? In the case of Meltdown, it will actually be a parent and a child process. So that's how we are going to set things up.
Okay.
It could be threads, but it depends on the context. That's all I will say.
That's why you were saying that they have to collude together, right?
Yes, correct.
So
correct.
they have to have something shared between them,
Correct.
legally shared.
Correct. In this particular case, in Meltdown, it is going to be colluding adversaries on both sides. Okay, so it's a covert channel has a. I think I got the definition mixed up at the beginning of the lecture. A covert channel actually has colluding adversaries on both sides. A side channel is one where one is a victim and one is the attacker.
Yeah.
So this is a covert channel. Okay, because they are colluding adversaries.
Thank you.
Yeah. Okay. All right. All right. So this is what this graph shows. So you can see like over here a plot of the access time in cycles to access every element of the probe array. The x-axis is the index of the probe array, and the y-axis is the amount of time in cycles to access elements of the probe array. And you can see actually a signal over here, which is that the X element is accessed, the access time is much smaller. Of course, it's not all going to be exactly the same, right? There is going to be some jitter, but you can see a very clear signal when the X element is accessed, and this will tell Alice that the X element is the one that Bob is trying to communicate to her. All right, so it's a smaller read time. So in that sense, this is a timing side channel where you're using the time of access of a memory word, for example, to be able to infer a secret that you're not otherwise supposed to obtain access to. There are other kinds of channels. Okay, so there is something called storage side channels where Bob can actually communicate to Alice. He can communicate. So let us say he wants to communicate some information. He breaks it down into bits. Okay, so he encodes it as a bit string, and he will communicate it to Alice bit by bit. Okay, so what he will do is that he will fill up the disk with a lot of garbage data, and if Alice tries to now write something to disk, she's going to get an error saying that storage is full. Okay, and that's how Alice gets a bit of 0, and then he will delete information which so that whenever Alice tries to write something, it will be successful, and that will be a communication of bit 1. Okay, so based upon whether the storage is full or not, Alice will be able to get a secret from Bob, a 0 or a 1, right? And that's called a storage channel, a storage side channel, or a storage covert channel through which Alice and Bob leak information. Okay, bit by bit, Bob will leak information to Alice. Okay, but we are going to be focusing on cache-based timing side channels, timing covert channels. Okay, yeah. So here's the definition: side and covert channels. In a covert channel, the attacker controls both ends of the timing channel, or both the participants on either side of the channel can collude with each other, and you can use this to transmit bits of information one end to the other. In a side channel, the ends need not cooperate, right? One is a victim, one is the attacker, and so Meltdown is going to use such a covert channel to read kernel memory from userland. So let's look at that. Okay, so here's an important building block, at least as far as meltdown goes, which is out of order execution. And this is a trick that's employed on all modern processors. So this out of order execution is a trick whereby instructions are allowed to execute speculatively based on data availability rather than executing them in program order. Okay, so your compiler may have produced code in some order, but your processor need not actually execute the instructions in that order. It can execute instructions as and when data becomes available. Okay, so this is the key to high performance, because when the program completes, in the sense that when the program starts, ultimately, the logical order in which the instruction should proceed is the instruction order that the compiler has generated, that you are actually providing to the processor. But the processor is free to execute them in any order that it deems fit based on data availability. So whenever it executes these instructions, it executes them speculatively and keeps them in internal buffers till the program's actual execution reaches that point, at which point it retires the instructions. In other words, it commits the state and makes it visible to the program. Okay, but the data is already ready. Whatever computations need to be done are stored in internal hardware state. They're already committed and made visible to the program when the program sort of reaches that point. Okay, so you don't have to actually waste cycles along the critical path. So let me give you an example. Right, so if you see these instructions over here, there is there are three instructions. There's a load, there's an add, and a subtract. Right, if you execute them in program order, you will have to first finish the load and then the add and then go for the subtract. Okay, so that means that the entire operation of subtraction, which takes a few cycles, will have to wait until the load and the add complete. But you notice over here that there is only a data dependency between the load and the add. The subtract does not depend on the load. So there's no reason why the subtract needs to wait for the load. The processor can go ahead and execute the subtract as long as these arguments are available, right? And it can wait for the load results to be ready, which might actually take some time if you're accessing memory. Okay, and then the add can actually execute after the load is complete, after the data is, let's say, loaded into the cache. So an out of order processor will feel free to execute things in this order. Okay, and then the results are only going to be committed in program order. Okay, so the results will seem as though the program executed in order. Okay, and this is a lot of engineering that goes into designing these out of order processors. In fact, in one of the first few lectures in any computer architecture course, you learn this famous algorithm called Tomasulo's algorithm that is used to implement this kind of out of order execution. Okay, so this is an example of a particular kind of out of order execution called dynamic scheduling. There is also another kind of out of order execution called branch prediction, where the processor sort of guesses what the outcome of an if then else statement will be and starts speculatively executing along the branch that it thinks will be taken. Okay, so if the true branch is taken, let's say 100 times out of 99 times out of 100, the processor keeps track of that by keeping track of which way a branch went, and it's going to start executing the true branch, right, under the assumption that the false branch is not going to be followed. And so when the program actually reaches the true branch, right, in the order in which instructions are committed, all of the computations on the true branch are now ready for use within the processor's internal state. Of course, if the program ends up taking the false branch, it will just discard the state. The processor just discards the state that's not made visible anyway, and then start executing from the false branch, right? Nothing lost, just some performance. But if you did take the true branch, you gained performance, right? That's the main advantage of doing things that way, and that's called branch prediction. These are all instances of speculative execution where the processor is going to guess that you're going to do something and keep the results ready for you, so that when you're there, right, it's all ready, right, for you to consume. In fact, this idea over here, as a small aside, is also now being used in modern, or it's being proposed for use in modern e-commerce companies, right? Which is that based on your past shopping behavior, they decide what kind of junk you're going to buy next and keep it ready in a go down next to your house, so that the minute you order it, ting tong, your bell rings, and then the product is right there within half an hour, and you're pleasantly surprised. But there's some AI that decides that, okay, here's your purchasing pattern, and you're going to purchase this product, and it's already been pre-delivered to your go down, even though you don't know about it. And when you order it, voila, it's there at your front door within 30 minutes. This is the way that the future is going to be. Of course, if you didn't buy it, it's a loss for the e-commerce company, but nothing lost, right? They'll just send it off elsewhere. The product is not really lost, but the idea is that they have pre-optimized it, and that's precisely an example of speculative execution. So the idea is that the instructions execute speculatively out of order, right? In whatever order the processor deems fit, but they are set to commit only when the speculative state is concretized via the actual execution. So the program counter actually lags behind the speculative state. The program counter reaches an instruction, and the speculative state matches what the actual state of the execution is. That's when it is committed. Okay. So the process of committing an instruction is also called retiring that instruction, which is that the results are now made available to the program, and the program can see it and it's committed, right? There's no way to walk back, because that's the result, and the program is to move on with that result in hand. Okay, so that's out of order execution. So let's look at the effects of out of order execution on the cache, right? So let's just take this simple 3-line code over here. In fact, it's 2 lines. So maybe this is a program, right? And statement number 1 is always going to throw an exception. That's what this raise exception is. Okay, it's always going to raise a hardware exception. Maybe in statement number 3, you're accessing, let us say, a probe array of the sort that I set up before, and it is maybe the probe array, every element is 4K bytes long. 4K is the size of a page, and it's set up intentionally like this. But any case, right? I will get to this detail later. But you're accessing something element in the probe array. Okay. Now, if the processor is going to speculate and execute statement number 3, it is, the exception, it doesn't actually, the exception is a software exception. The hardware doesn't really know about it. It decides to actually speculatively execute things and accesses the probe array. This data is actually going to be loaded in the cache. Okay. So speculative execution, even though you don't see the effects of speculative execution in the program, in the sense that no variable or register is going to actually change its value on the basis of speculative execution, at least no programmer visible or no program visible memory or register is going to change its state on the basis of speculative execution. The internal microarchitectural state does change. Caches, the state of the cache will change based upon speculative execution. And so if this statement number 3 was ever accessed by a speculative branch, this data will be brought into the cache. Okay, so even though this statement number 3 will never be reached in any real execution, because statement number 1 will always throw an exception, a speculative execution has no problem actually executing statement number 3. And so that is the problem. That's the root of the problem. Okay, so we will see how it works in Meltdown. Okay, let me just skip this slide. It just shows you what happens, right? You can actually see the effects of the speculative execution. Some cache lines some things will be loaded in the cache and some are not. Okay, so now let's look at Meltdown and let's look at the setup. Okay, so the setup in Meltdown is that it's a covert channel, and one process is going to actually going to try and read kernel memory, and it's going to read that kernel memory. That's what is going to be denoted by secret over here, because a user process is never supposed to access kernel memory. And so we will denote that by this term called secret. And that is going to be the first process. So these dotted boundaries over here are actually processes. So this is process number 1. This is process number 2. Okay. Now, process number 1 is going to run some code, and we are going to see that. And the code that it's going to run, we are going to call them transient instructions, in the sense that those instructions in any real execution will always throw an exception and fail. Okay. So, but what they end up doing if executed speculatively is that they end up inducing a change in the microarchitecture. Okay. And there's going to be another process that is actually going to take that microarchitectural change and concretize it into real architectural state. So what do I mean by that? What I mean by that is exactly this, which is in this Alice-Bob attack, what did Bob do? Bob effected a change in the microarchitecture by going and reading an element of this cache and bringing it into the cache, right? He read the Xth element and brought it into the cache. But the value X was never written anywhere directly to Alice. Now, Alice is somehow getting the value X by reading every element of this probe array. And just because one of the elements took slightly less time, she is able to infer that the index X took less time. And therefore, the index X becomes something that was implicit in the microarchitectural state to something that is explicit now that she can actually store as a variable, right? She can store the value X, the value of X in a variable. So that's now called taking the microarchitectural state and making it concrete. Okay, so we are going to have a second process that does that. Okay, and that is how we are going to set up Meltdown. Now, I'm going to describe to you a particular setup where this process over here is going to be a parent process, and this is going to be a child process. And so this one forks this, but this one is going to do something that is going to end up killing the process. Okay, so the transient instructions are going to end up causing an exception, and this process dies unless there is some exception handling code. You can always add exception handling code, catch signals, and of course go to the next loop. That's possible. But the point is that this instruction sequence will never succeed in doing what it aims to do. But what it will do is that it will affect a microarchitectural state change, and the child process is going to be able to read it. Now, when you read the paper, you will also read that there are other ways to do this other than just parent and child process. In particular, they talk about a concept called transactional memory, which is now available in a processor extension in Intel called TSX. If you don't understand transactional memory, no worries. You can feel free to gloss over that part, but at least try to get the parent-child based architecture of this of the overall Meltdown attack. Okay, what I'm going to do next is delve into actually what these transient instructions are as well, but this is the overall setup of the attack. Okay, and let's see how now the attack works. Okay, so the secret, as I said, is a value of interest. In this particular case, in Meltdown, this value of interest is going to be a word in kernel memory. In general, the user space is not supposed to read anything in kernel memory. So any byte of kernel memory is supposed to be secret. And so we can just think about any byte in kernel memory as being the secret that we are thinking about over here. Okay. In fact, I got it reversed, right? So this guy is the parent process is a child. The child always dies. The parent doesn't die. That's just how they set it up. The child, the parent actually starts up and is the one that's going to recover the secret. It's going to fork a child. The child is always going to try to read the secret. It's going to be unsuccessful and die, but the parent is going to be able to read the state that the child tried to make concrete. Okay. In the previous slide, I mistakenly said this is a parent and this is a child. It's the other way that they have set it up, but that's okay. All right. Okay. So here's the full attack. Okay. As I said, it is 5 lines of code, of which we are going to ignore 3 lines. We are just going to look at the crux of the attack. This is the Meltdown attack. Okay. 2 of the lines are comments, as you can see. The first 2 lines are just comments. 3, 4, 5, 6, 7 implement the full attack. All right. So what is the goal of this attack? As I said, it is to try to read kernel memory, right? And what we are going to do is the following. So like in the Alice-Bob example, right, the parent and the child are going to set up a probe array that they are going to use to communicate with each other, okay, or to concretize the microarchitectural state. Okay, and the probe array is going to be set up exactly in the way that I spoke about before, in the sense that every access to an element of this probe array is going to end up accessing a different cache line. All right, it's not the same cache line, it's a different cache line. And that's going to be stored in RBX. RBX stores the address of the first element of the probe array. Okay, and RCX, which is another register, is going to store the kernel address whose contents you want to read. Okay, so the secret that you want to read is stored in star of RCX. Think about it that way, right? RCX is going to store a kernel address, the contents of which you want to read. That's the objective of the attack. Now you might ask me, what good will it accomplish if you read just one kernel address, the contents of one kernel memory location? And the answer is that you can't really do much by reading one kernel memory location. In order to implement a real attack, the way you would implement it is by actually iterating through every word in memory. Okay, so the way that this attack would work is that you would read the value of one memory location and repeat this attack for every location in memory, thereby reading the contents of all of memory. Okay, so you'll have to repeat this attack as many times as you want to be able to read the contents of all of memory. Okay, so let's look at the attack, right? It's 3, 4, 5, 6, 7. At the end of the day, it is just a loop over here, right? The body of the loop is statement 4 and 5. That's it, right? So 4 and 5 are the main body of the attack. You're just going to be retrying it a number of times. I'll tell you why shortly. Okay, so let's look at line 4 and start, right? So the goal of the meltdown attack is that the attacker wants to learn the value of a byte that is stored at a particular kernel memory address. In this particular case, the address is stored in the RCX register, as I already explained in the previous slide. So let's read the attack by focusing on line 4. 3 and 6 are just the loop retries, and so we'll start with line number 4. Okay, so in line number 4, so how is the attack set up? The attack is set up so that the child process is going to execute this code, and the parent process recovers this microarchitectural state change and concretizes it. Okay, so the child is executing this. So the child reads the secret in the sense that it tries to execute this instruction, move AL, the value that is stored in this particular RCX. Okay, so RCX is the address, and you're dereferencing it over here. And you're saying, hey, take whatever value is stored in RCX, the byte that's stored in RCX, and then copy it to this AL. AL is just the least significant bit of the RAX register. Okay, so that's what this says. Okay, store the byte value of RCX, whatever is in RCX into AL. Now, what can you say about executing this line 4 if you are in user mode? So if you are in user mode and you try to execute line number 4, okay, it should always cause an exception. The reason it should always cause an exception is because you're trying to access a kernel address from user space. Okay, so this is an instruction that will always fail. Without any sort of it will fail, right? If in any concrete execution, it will fail. Okay, but the problem is that if you use out of order execution and the hardware is not keeping track of which instructions will always fail, the exception status of the instruction, which is what Intel ended up doing, it will end up taking the next statement and executing it speculatively. Okay, so that's what it did. Okay, so the exception is handled only when line 4 is retired. Only when the line 4 is going to be committed, at that point will the hardware realize that there's going to be an exception. Okay, and it will say, hey, line 4, there's a mistake, so kill the program. But the problem is, because the Intel processor did not realize or did not keep track of the fact that this instruction is going to throw an exception, when it's doing speculative execution, it starts doing out of order execution and starts executing lines after that, which in turn affects the microarchitectural state. There's nothing wrong in what Intel did. As far as Intel is concerned, it did not keep track of the exception status, and it chose not to, because when the processor execution reaches over here, anyway that instruction is going to kill the program, right? It's not going to be visible to the programmer. What they did realize was that in affecting the microarchitectural state change, somebody could implement an attack like this. Now, AMD processors were saved from Intel precisely because they implemented the microarchitecture differently and kept track of the exception state and did not employ out-of-order execution for any instructions that could potentially raise an exception. Okay, so they chose that policy of doing it. No particular reason why, not because they were aware of meltdown or the possibility of meltdown. They just chose to implement it that way. And so they were immune from this attack just by chance, right? But Intel said, hey, we will do out-of-order execution. Anyway, we are going to track exception status when we reach concrete execution. At that point, we'll deal with it. But the problem is that the microarchitecture has already been, state has already been changed and it's too late. Okay, so that is line 4. It tries to access this kernel memory. Let's look at line 5 now. Okay, now the way that this probe array is set up is that at least in this particular meltdown attack, the probe array, every element is 4096 bytes long. Okay, so it's page aligned. So every element of the array is one full page, virtual page long. So it's 4K bytes long. Okay, so that's the way the probe array was set up for the meltdown attack. So what this line 5 is doing is that all it's doing is that it's taking this RAX and it's shifting left by 12 bytes. Okay, so what is shifting left by 12 bytes? Well, you're multiplying the byte value by the page size, and what that helps you do is that it allows you to get the address of the X element in the probe array, right? How do you get the address of the X element in an array, each of whose elements is 4K long? Well, multiply the value of X by 4K. That's exactly what they do over here in line number 5. Okay, so that's used to index the probe array. Okay, so the reason that this large spatial distance was maintained, why did they choose 4K size pages? The reason that they did was to avoid another optimization in processors, which is that of spatial locality. Typically what caches do is that if they load a word, they also load the neighboring words. Okay, and in order to avoid that, they sort of did this, where every 4K bytes is the size of an element. Okay, so the probe array size is actually 256 multiplied by 4K bytes. And why is it 256? The reason it's 256 elements is because you're going to communicate the contents of memory byte by byte. How many bytes are there? There are 256 possible bytes, right? 8 bits, 256 values. So that is all you have to communicate. If you want to communicate the value of a byte, it is only one of 256 values. And your goal here is to communicate one of those 256 values. So your probe array is 256 times the size of each element, which is 4K. And so that's the size of the probe array that's set up. Okay, so I'm going to skip over why that loop exists until the next slide, but let's go to line number 7. So line number 7 is transmitting the attack, okay, transmitting the value. So what does line 7 do? Well, it's trying to move into RBX, the word from RBX plus RAX. What is RBX? RBX is the first address of the probe array. What's RAX? RAX is the offset of the element that you're trying to communicate, the Xth element. Remember, that's what we did in line 5. We calculated the address of the Xth element. Now, the address of the beginning of the array plus the offset for the Xth element gives you exactly what you're trying to access, and you're saying move that to RBX. Okay. Now, what this will do is that this will read the probe array, the Xth element of the probe array. Precisely this access over here reads the Xth element of the probe array and brings it into the cache line. Okay, so now the cache is affected by the very fact that you're trying to read that Xth element. This is the line over here that affects the cache, brings the word into the cache line, and on the parent side, what you do? Well, you just iterate through this probe array and then try to figure out which word was accessed, which word was not, and only probe array of X will be a hit in the cache, and therefore the attacker learns the value of X. Okay, so that's the meltdown attack. That's it. Now, what's the role of this line 3 and line 6? There's a loop over here. So the paper actually talks about this in rather detail. This is to make the attack more robust. It so turns out that, when you're implementing this attack, you're actually in a race with the processor, right? The processor should not commit the instruction before you've been able to affect the microarchitectural state change. So the attacker is in a race against the hardware, and you should be able to get the transient instructions to finish executing and actually change the state of the cache before the exception on line 4 is thrown. Line 4 will always throw an exception. Okay. And what happens is that in some machines, this exception is not handled and the process crashes, but the processor essentially ends up zeroing out the registers before crashing the process. So all the registers become 0. Okay. So the problem is that if the zeroing out happens faster than this operation on line 5, the attacker will read the wrong value for X. Okay. So when you implement this attack, you end up, in fact, you have to win a race. You don't always win the race. And so when you read the value of the register, you'll see a whole bunch of zeros and you'll see the actual signal, which is the value of X. And so this loop over here is to reduce this zero noise bias. If it's 0, right, just keep retrying. Okay. Right, sufficiently many times. If the actual value is 0, you can't do much about it, right? At some point you'll say, okay, give up. That's not here. You'll try for a number of times. When you get a non-zero value, that's the value you're trying to read, and then get out, right? And then read it. So that's called zero noise bias, and this explanation is in the paper. This is to make the attack more robust, where you are trying to win a race against the hardware in sort of trying to get the microarchitectural state committed before the instruction actually throws an exception. Okay, so what's the implication of the meltdown attack? Well, it's memory dumps, right? You can iterate through all of memory and obtain a complete dump of the memory of the kernel. And as I was explaining earlier in the lecture, physical memory is also typically mapped at an offset within the kernel nowadays, especially when there is an abundance of virtual memory. So by dumping kernel memory, you're able to obtain a complete dump of physical memory also. And that is basically the worst kind of attack that you can imagine, the most dangerous game over kind of attack that you can imagine. Okay, so here are some examples that were illustrated in the paper. They showed how you are able to, and what does the attack involve? The attack involves nothing. It just involves downloading a piece of code that is going to set up a probe array and then execute it on your machine, right? It's not really malicious code. It's just going to access some probe array, some weird array that it's setting up and accessing it. And so they showed an attack against Firefox version 56. This was 3 years old Ubuntu, okay? And what you see over here is the Firefox window with a memory dump of what they were able to read. And if you're able to parse the memory dump, essentially what they were able to get was, so when you load a browser in memory, right, typically you have got saved passwords and so on. Many of you might be using saved passwords. They were able to recover saved passwords for various websites, right? Of course, their own attack, their own browser, but they show what this program is capable of doing. It's capable of reading secrets in another process that's sitting there in memory. Why? Because they were able to attack the kernel. And the kernel stores all of the secrets of the other processes, right? So they were able to get the passwords. Okay, so that's the meltdown attack. So there is actually a defense for this. This defense is called KPTI. If you do a Google search for it, there are a lot of articles about KPTI. It's in fact now part of the mainstream Linux kernel also. But what does it do? Let me give you an idea, right? So the meltdown attack happened because the kernel space is loaded into the process address space, and all of kernel memory is also loaded into the process virtual address space. And so the basic thesis behind KPTI is, why should that be the case? If the kernel was not mapped into the user address space, then even if you did have a meltdown attack, you would not be able to dereference that kernel memory because it doesn't even exist. It's not even mapped into the kernel address space. So why even map it, right? So what KPTI does is that it provides two views of virtual memory for every process. You get this particular view when the process is in kernel mode, that is when you have executed a system call, and you need that because you need to be able to access all of kernel memory. But when you go into user mode, a lot of the kernel space is not going to be visible. The only portion of the kernel space that's going to be visible is the bare minimum that you need for execution. For example, the addresses of the system calls and the entry points into the system calls. The stubs of the system calls are going to be visible to the user space, but nothing else is going to be visible to user space. What does that mean? That essentially means okay, again, I lost internet connection for some reason. I'm back on. Let me just repeat. What this means is that, whenever this process is in user mode, those corresponding pages of kernel memory are not even going to be mapped into user space. Okay. So the page tables will just say that those pages are unmapped. Okay. So you have two different views of a process based upon whether that process is in user mode or kernel mode. But of course, now there is an overhead. The overhead is that of switching page tables every time you go back and forth. That costs time because every time you have to change the page table base register, and now of course there are going to be more entries in the translation look aside buffer and so on. Okay, so it does have real performance implications. Um, and so the long-term effectiveness of the solution is unclear in the sense that if you're really running a performance critical program, would you adopt KPTI as a defense? You don't know. But it is available. The code is there. It's available as a in the mainstream Linux kernel. Okay, so that's Meltdown. In the 15 minutes or so that I have, let me just talk about Spectre, which is in a very quick manner. But summary of Meltdown, right? No host program is required. There is no vulnerability that you're trying to exploit. It's self-contained with the parent and child attacking process. And only Intel processors were affected. The main reason is because they chose not to look at exception status when doing speculative execution. Okay. All right. So let's look at Spectre. So Spectre is much more widespread in the sense that it affects Intel, ARM, AMD, everything. It uses a slightly different attack vector, and the attack vector is here is branch prediction, and it's slightly harder to deploy than Meltdown. I'm only telling you about this because Spectre and Meltdown were from the same group, and they came out at the same time. The Spectre paper has not been assigned as reading for you for this course. Only Meltdown is. But I want to tell you about the attack anyway, right? And it's slightly harder to deploy than Meltdown in the sense that you do require a host program which contains a certain instruction sequence that can be misused. But it's more dangerous than Meltdown in the sense that there's no known fix to date. Okay, so the out of order and so the building block here is that of branch prediction, right? So in out of order execution, what happens when the processor reaches a branch? Well, the hardware branch predictor takes over and then it predicts the likely outcome of the branch based on the past execution history of the program, and it speculates around the likely taken branch. Okay, so when you execute this particular instruction stream speculatively, when you reach this jump, maybe the true branch has been executed all of the time in the past, and so the processor says, okay, this time also it's likely to be true, and let me start executing that way. Okay, so the concrete execution might be over here, but the speculative execution in the processor may have gone ahead. And so the speculation may proceed along the true branch, but the concrete execution may actually end up taking the false branch. Okay. So the host program, what you need is to find this instruction sequence with a branch, and you have to train the branch predictor. So the processor, you have to run the program a number of times so that the branch goes in a particular direction. Let's say true. Okay. So that is the preparation phase for the attack. And in the actual attack, you're going to feed a malicious input that actually causes the branch to go in the other way. Okay, in the other way than what you've trained the branch predictor to do. So maybe it actually goes along the false direction. But in training the hardware, you have sort of forced the hardware speculative execution state to go along the true branch and execute speculative instructions along the true branch. Okay, and therefore you affect the microarchitectural state that way. That's how it works. Okay, so here's an example. So supposing you have a host program with this particular snippet, right? If x less than array 1 size, y equal to array 2 of array 1 of x times 256. This is again a probe arrays. Okay, so array 1 size, the unsigned byte array of size array 1 size, doesn't exactly matter what this is, and array 2 size is 256 times 256, 64 kilobytes. Okay, so let's say that this value x is derived from user input, okay, and therefore it's controlled by the attacker. What you're doing over here is that if you access the array legally, which means you're only going to try to access things within the array bounds, it always goes in the true branch. Okay, if you ever access things that are outside of the array, array 1 size, that is out of bounds access, this statement is never going to be executed. Okay, but you just speculate, right? I mean, you don't know what the branch is going to take. I mean, the direction of the branch. The hardware just executes these instructions, assuming that things will go true, right? In the rare instance that it goes false, if you give a value of x that's larger than array 1 size, this access is illegal, so it will never go here in any concrete execution. But if you speculatively execute it, you'll end up accessing things, at least in the speculative execution, that are outside of array 1. Okay, so in this program, let's say there is some secret data that you wish to access, and this data over here that you wish to access is some location, some distance away from this array 1. Okay, so array 1 is of size array 1 size, and there is from this end of the array, you know that the secret S is sitting, and you want to access it. Okay, and so array 1 of this actually obtains this value S. So what you do in the attack is that you execute this program enough number of times so that the value of x is less than array 1 size, and you always take the true branch. So the processor is fooled into thinking, oh, most of the time the true branch is going to be taken. Then you arrange for the cache to not contain array 2 and array 1 size. Okay, and you arrange for the cache to actually contain the secret value S. How? Well, maybe S is some sort of a cryptographic key, and you're going to use it in some cryptographic computation, and so the value of this S is going to be loaded into the cache. You can arrange for these things. As you can see, there's a lot of preparation. That's why it's a harder attack. And then what you do is that you execute the program with x equal to dis, which is the distance away from the beginning of array 1 that the secret S is in memory. Okay, so x less than array 1 size, right? I mean, this array 1 size is a variable. Because this variable is has been evicted from the cache in the previous step over here, the time that you try to access this variable over here, that will lead to a cache miss. Okay, that leads to a delay in fetching this, and the processor essentially speculates on this branch. It says, hey, okay, I do not yet have this. I'm going to go and fetch it. But hey, in the meanwhile, I think that you're going to take the true branch. Just let's go and execute the true branch. So what does the true branch end up doing? Well, it ends up executing array 1 of this, which is a hit in the cache, the value of S, and then proceeds to read array 2 of S of 256, which is a miss in the cache. Okay, but array 1 size may have arrived by then, and then the processor realizes that there's a mistake in the speculation, but it's too late because you've already read S times 256, which is this probe array that you have set up, and you have affected the cache state. Now on the other side, the attacker will just go and read all the elements of array 2 and figure out which one is taking less time, and therefore figure the value of the secret byte S. That's how Spectre works. Okay. So if array 2 is accessible to the attacker, you just probe all of the elements exactly as you did in Meltdown and use cache timing to figure out the value of S. Okay. So it is, I showed it to you with a very convenient code sequence, but it does not have to be actually so conveniently set up. You can actually search for gadgets, just like we did in Drop, that can be weaved to achieve this this desired effect. Okay. And again, it's not restricted to conditional branches alone. People have also done it for indirect branches. Again, all of this is the Spectre paper. If you Google Spectre, you'll get the paper, but it's not assigned reading for this course. So I'm not going to actually require you to read it. Okay, and as I already told you in the beginning of the lecture, one important implication of Spectre attacks is breaking out of sandboxes. So sandboxes are set up exactly in this way, where the legal things to be accessed are in blue. That's where you should play. This is the sandbox, and you're not allowed to access anything outside the sandbox. And for example, JavaScript in a browser, but they show actually that you can exit the JavaScript sandbox in a real browser using the speculative execution technology and access things outside of the sandbox. Okay, same basic idea, but of course the actual attack is a much more detailed engineering exercise than the simple example that I showed you. Anyway, so that is Spectre, but of course, you are only going to be responsible for Meltdown, but you see how the attack landscape has sort of evolved. Okay, so that ends the class. Let me just turn the recording off and then just take a couple of minutes of questions.